We're continuing with particle equilibrium. Earlier, we worked a number of example problems in 2D particle equilibrium, starting with pretty easy problems and working our way to some more complex problems that applied a lot of interesting principles, including stresses, method of joints. In this next sequence of problems, we're going to work a number of 3D particle equilibrium problems. And again, we're going to work progressively from some fairly simple problems to some harder ones as well. And so this first problem is a typical exam problem in that you can solve for something using one equation. So what we have is, so remember for 3D particle equilibrium problem, so remember for 3D particle equilibrium, I can write three equations of equilibrium. I can sum forces x equals 0, sum forces y equals 0, and sum forces z equals 0. So I have three scalar equations, or I can just write the sum of the vector equations is equal to 0. These three scalar equations are contained in this vector equation. So, and these apply to a concurrent force system, which means the forces all act at a point. So I can solve for up to three unknowns, and they have to be forces that act at a point. And so that's what's going on. So this is a good test problem in that all three forces do not have x, y, and z components. If you look at one of the later problems that will work, I mean, this is like the last problem that we're going to work. I've got three struts. I've got a force acting up here. And all three of these, and there's a force that acts along each of these struts. But all three of these forces have x, y, and z components. So you end up with a full 3x3 matrix that you have to solve. And so that gets relatively complex. This problem here, TA, lies in the z negative y plane. TB acts in the z negative x plane. And so this just has two components. This just has two components. TC, I'm giving you the magnitude of him, and I'm giving you the direction in spherical coordinates. And so remember spherical coordinates. Basically, you have a force. This is x, this is y, this is z. I have a force vector out here in space, and it has a projection down to the xy plane. And this angle to this projection is a positive theta. And this angle down from z